Hello everybody. In this video, we're going to work through a proof of what's known as Euler's identity, and all you need to know is that the following are formulas for Maclaurin polynomials, assuming that you start at n equals 0. We have e to the x being equal to 1 plus x squared over 2 factorial, and it goes on with the power of x going up by 1 and the factorial going up by 1. And we have our sine of x and cosine of x polynomials, the sine of x polynomial being x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. It's an alternating series using only odd powers of x and odd numbered factorials. And cosine of x kind of fills in those blanks. Starts at 1 minus x squared over 2 factorial. It's all the even powers of x over all the even factorials. And when you look at these three polynomials, these three expansions, it looks like you can come close to saying that e to the x is equal to sine of x plus cosine of x. But the problem with that is it's the alternating signs in sine and cosine that stop those two from being equal. And in fact, if you look at the sine of x polynomial plus the cosine of x polynomial, you get 1 plus x minus x squared over 2 factorial minus x cubed over 3 factorial, and so on. And the signs don't exactly alternate, at least not one after the other. The polynomial starts off positive, positive, then negative, negative, and then keeps going in that pattern, 2 positives for every 2 negatives. And so I want you to think about is there anything else that you've ever learned about that follows this sign pattern? And there should be one thing that sticks out, and that is the powers of the imaginary number I. Recall that I is equal to the square root of -1, so I squared would be equal to -1 itself, I cubed would be equal to -I, and I to the 4th would equal +1. And it goes in a loop of those 4 powers. For the next powers, I to the 5th would be the same as I to the 6th would be the same as I squared, I to the 7th would be the same as I to the 3rd, and I to the 8th would be the same as I to the 4th. So having established that these polynomials are equal to these functions, and noticing this pattern, the mathematician Leonhard Euler came along and said, well, I can develop that same sign pattern if instead of using just e to the x, I expand the polynomial using e to the ix, which means everywhere I see an x in that polynomial, I'll just replace it with ix. So we get an expansion that now looks like 1 plus ix plus the quantity ix squared over 2 factorial plus ix cubed over 3 factorial, and so on down the line. Which then would simplify to 1 plus ix, but when he reached the quantity ix squared, I is equal to -1, so that term would become -x squared over 2 factorial. In the next term, the I cubed part of that expression would become -I, so he ended up with -I times x cubed over 3 factorial. I to the 4th became a +1, so the next term would be x to the 4th over 4 factorial. And he would be able to continue in that loop. It would look like all the terms for the expansion of e to the x, but with that rotation of the powers of I. For the next 3 terms, the x to the 5th, 6th, and 7th terms, he would get I, -1, and -I, and this would continue on to infinity. And if you isolate that first term 1 and the even powers of x, notice that those are simply the terms for the Maclaurin polynomial for cosine of x. So e to the ix would equal cosine of x plus something else. And that something else, looking at the remaining terms, you have ix minus I times x cubed over 3 factorial plus I times x to the 5th over 5 factorial. Well, that's just the polynomial expansion for sine of x times the number I. And you get this overall identity that e to the ix equals cosine of x plus I times sine of x, which led to his most famous application of this identity. What happens when you evaluate it at x equals pi? Evaluating at pi, you would get that e to the I pi equals cosine of pi plus I times sine of pi, which leads to what's become known as Euler's identity. Simplifying this expression down, you would get e to the I pi equals cosine of pi, which is -1, plus I times sine of pi, or I times 0, and this would imply that e to the I pi must be equal to -1, or that e to the I pi plus 1 must equal 0. So is this a real application that has any extra meaning to anything real? No. By its definition, it involves imaginary numbers. It's an imaginary identity. But it comes from that power of knowing that we've generated polynomials that, if they go out to an infinite number of terms, are exactly equal to known functions. So just a fun creative use of what you would have already picked up on Maclaurin polynomials, and I hope you found that a little bit interesting. Thank you for watching.